Our next speaker is Shun Karato, and we're going to move. Well, we're going to go into the deep mantle now. I'm going to talk about melting in the deep mantle.
Okay. Yeah. Thank you for inviting me. It's my pleasure to come here, but in a way it's an embarrassment because I don't do anything like mathematical sciences, and then I have done very little about melting. So I thought about before I came here. Oh, okay. And then melting in the deep mantle. Maybe I can come up with some story. Okay. So what you're going to hear is very different from the previous talk. So our presentation at the Institute of Mathematical Science without any equations. Okay. So this is the kind of main points that I like to emphasize. The first point is that, well, that's kind of obvious for geologists, but partial melting and resultant melt-solid segregation are the main processes of chemical evolution of the Earth, which we know. But the second point is perhaps little, I don't know why. Second point is perhaps a little new. That is, the partial melting is ubiquitous throughout the mantle. If you look at the recent experimental results, including by our own results, in a way, it's very difficult to avoid partial melting throughout the mantle except for lithosphere because of the presence of volatiles. Okay? So melting is not limited to the asthenosphere. This is a very important message based on very solid experimental results, not only my own, but many other people. And another also very important thing, which I'm sure someone else discovered, but we confirmed, is that the nature of chemical evolution by partial melting is very strongly dependent on the depth or pressure at which melting occurs. In the shallow part, when partial melting occurs, melts are rich in silica component, like a basaltic melt. But if you do this partial melting in the lower mantle, completely opposite. You create a melt very enriched with MgFeO. In one experiment, residual is pure silica. So it's completely different trend of chemical evolution, which is extremely important for the evolution of the Earth's interior. And another point is, which has been already discussed throughout this workshop, is in many cases, the melt fraction, it's very important to distinguish melt fraction and degree of melting, but melt fraction is very small, typically less than 1%. Partly controlled by the volatile content, but partly controlled by melt transport. Melt fraction is very small, so therefore, it is not easy to detect partial melting by conventional or typical geophysical observations. And to address the possible detection of melt and the fate of melting, consequence of partial melting at small melt fraction, we really need to understand a process of melt segregation and other things, melt properties. For instance, density of melt. Very simple thing, such as the density of melt, is not quite well understood. Based on regular experience, you may think of partial melt is light, and that's why the melt makes volcano on the surface. But if melting occurs in a deep mantle, this is not entirely clear. Melt might be denser, so melt should go down. So therefore, understanding melt segregation processes, and then first of all, keep physical properties, is a key to understand the evolution of the Earth, based partly connected to the melting business. So outline is, first I would like to summarize where could melting occur in the mantle, including the shallow mantle melting, which is pretty well understood, but also the possible melting in the deep mantle, including transition zone and the lower mantle. And second, in relation to the place where the melting might occur, I'd like to discuss briefly what is the consequence of the mantle melting, such as a simple question such as, where does melt go, up or down, which depends on relative density of the melt relative to coexisting solids. And Yeah, and also how does melting affect the chemical evolution, which is connected to the issue of chemical segregation, chemical difference between the melt and solid. As I said earlier, rather surprisingly, very interestingly, the chemical difference between melt and solid depends very strongly on the pressure. And last point, which I'd like to discuss several times, is how to detect partial melting. As already you have heard, there are some indications suggesting that detecting melt is not as easy as we thought, like 30 years ago. And I'm going to show you some historical evolution of understanding this business, starting from 1964. And if direct detection of melt is very difficult, we might use as an alternative indirect method of inferring melting event, such as the chemical layering. Because chemical layering is extremely impossible, extremely difficult if partial melting doesn't occur and the mantle convects without any melting. So the outline is, yeah, and then so this, yeah. So partial melting in the shallow mantle. This part is pretty well known, as I said earlier. So this is one diagram to show depths and adiabatic temperature and melting temperature. And when materials move upwards, more or less adiabatically, and then at certain point melting occurs, because melting temperature increases with depths, but adiabatic temperature doesn't increase with depths as much as melting temperature. And then you may create partial melting. And in some cases, you can calculate the melt fraction. In this case, this is based on phase diagram. If you do laboratory experiments, you can find out how much melt you have at a given pressure and temperature conditions. And if you assume Earth doesn't have any gravity, you can directly translate this to this map. This is what was done in this paper. And then you find that large portion of atmosphere, fraction of melt is very small. This is due to the fact that melting in these regions, that is majority of the atmosphere, is caused by the presence of volatile elements such as water or carbon dioxide. If you go to deep mantle, melting temperature measurements are difficult, but last several years in several laboratories. Experimental results were published to show how melting temperature changes under the conditions where volatiles are not present. Under those conditions, melting temperature profile is pretty well established. And if you look at the, for instance, this diagram, this is the result by Hike et al. They did diamond anvil experiments, put sample into very high pressure and temperature, and they detect melting event. And then they found that without any volatiles, the melting starts at those temperature, like this is in terms of depths, 600 kilometer depths, and going down to the bottom of the mantle to almost 3,000 kilometer depths. Melting temperature goes from 3,000 K to something like 4,000 K. This is solidus, and the liquidus is like that. And then if you compare those melting temperatures, solidus and the liquidus, with the plausible temperature profiles in the Earth, such as this, then you would conclude that in the majority of the deep mantle, melting is impossible without any volatiles. So with a volatile-free composition, melting in the deep mantle is impossible, except possibly at the very bottom of the mantle. So this is the first order conclusion you should get. However, if you add some volatiles, such as the water, melting can be enhanced. There are several experimental data to show this. One is the paper by Inoue 20 years ago or so, showing that melting of this mineral, olivine, without any water at 12 GPa, you need this much of temperature. 2000 or 2200, something like this temperature, without water. But if you have water, melting temperature solidus can be reduced down to 1200 degrees. Enormous effect of the water to reduce melting temperature. We did similar experiments. Actually, in these experiments, we didn't plan to melt the experiments. We tried to something else, and then unfortunately or fortunately, melting occurred. So we changed the direction, research direction, to look at the melting. And amazingly, melting occurred under those conditions, 25 GPa, lower mantle, at a temperature of 1600 degrees C. And then later on, we repeated the experiments to find that melting with water at this pressure, lower mantle, is possible even at temperature of 1400 degrees C. Typical temperature at the top of the lower mantle is 1600 degrees C. So therefore, with these experiments, you conclude that with the presence of water, it is very hard to avoid melting. And yeah, so the water enhanced melting. And also, after the melting occurred with water at those very high pressure conditions, composition of both melt and residual solid are very different from the melt and residual solid caused by partial melting at shallow conditions.
How much water is in there?
This one is 5%, I guess. Yeah, we changed. Yeah. Yeah, so it's of course much higher than the typical Earth, but you can construct some phase diagram to discuss something. So the water enhanced melting occurs because fundamental reason for water enhanced melting is water prefers to go to the liquid, and then there's a little bit, only small amount of water goes to mineral. Because large amount of water goes to liquid, and then liquid's entropy, disorder, degree of disorder increases, and then free energy drops. So that's a fundamental reason why water, some other impurities, enhance melting. What this means is that if the solid part has some solubility of water, then this water enhanced melting would not occur. So the condition at which water-enhanced melting occurs is very critically dependent upon solubility of water in solid component. And if you plot the solubility of water in solid minerals as a function of depth, you find that there is a distinct peak at transition zone. In the shallow mantle, upper mantle, solubility of water increases with depth to something like 0.1%. But in the transition zone, solubility is as high as 2 or 3 weight%, and then if you go to lower mantle, solubility decreases. And this distinct solubility profile causes plausible melting due to the vertical material motion. Imagine if you have a material moving from down, from deep to up through the transition zone, and if the materials have certain amount of water, relatively large amount of water, even with a relatively large amount of water, material is going to be happy and no melting in transition zone because solubility is so high. But as soon as these materials goes up to the upper mantle, solubility is so low, and therefore melting starts. Similar thing should happen if the water-rich materials go from transition zone to down. Okay? So the partial melting across the transition zone and upper mantle and transition zone and lower mantle is a very likely possibility caused mainly by this particular water solubility versus depth profile. Okay? So deep mantle melting, as I said earlier, is nearly impossible if there's no volatile. However, if some volatiles are present, then melting could occur. Because of this fact, degree of amount of melt you can create in the deep mantle is limited by the amount of volatile you have. And in general, we do not know exactly how much volatiles we have in the Earth, but in general, based on some sketchy estimates from geochemistry, amount of volatile we expect is relatively small, like 0.1 or 0.01 weight percent. Okay? As a consequence, any partial melting in the deep mantle, melt fraction must be very small. However, as we discussed several times through the workshop, the amount of melt we have or we expect in certain point is not only determined by just melting relationship, but also determined by the transport processes of the melt. You may have melt accumulation in certain point, so therefore there's a very strong need to understand the processes of melt transportation. And as I said earlier, whatever the processes of melt formation or melt transportation, amount of melt we expect in a deep mantle is expected to be small. So the detecting melt from geophysical method is going to be extremely challenging. As I mentioned to you earlier, partial melting is a very important process to control the chemical evolution. And the way in which chemical evolution occurs is controlled by chemistry of melt and solid. And when you do melting experiments like this at lower mantle conditions, we started from perovskite, bridgemanite materials with some water, and at the end of the experiments, we found that large fraction of materials goes to melt, coexisting with some solid material. This one is the bridgemanite and stishovite. And then we determine the chemistry of solid part and liquid part to understand what kind of chemical segregations occur caused by deep mantle melting. This is the result of those analysis. Key point is that if you compare the melt and solid, this is solid, the magnesium to silicon ratio is very different. In other words, the melt is very high ratio. That is, compared to the solid, melt has higher magnesium and MgO and FeO than the starting material. This is completely opposite to the trend of chemical evolution caused by shallow mantle melting. And for instance, if you sketch the direction of chemical evolution in a shallow mantle, if you start from this condition, melt is going to be enriched with iron and silica. So the melt has this composition and the residual goes to this direction. In contrast, if you do the same thing in the lower mantle, melt composition is towards this direction, Mg and FeO rich and SiO poor. And then residual should be silica rich. So the evolution trend that happen in the deep mantle melting is completely opposite to the evolutionary trend which should happen in the shallow mantle melting. So when you make partial melting and when you make a melt and solid with different chemistry, then this is a potentially very important way for chemical evolution. However, to make chemical evolution, you have to separate melt and solid. The first question is, which way does melt go? So this is a question of melt density relative to solid density. The bottom line is there are two things actually which control this density business. First point is melt is in general much more compressible than minerals. In terms of bulk modulus of various minerals at ambient conditions is on the order of 100 GPa. But bulk moduli of various melts at low pressure conditions are 20 GPa or 30, amazingly low. We developed theory to explain this, and this causes the very rapid compression of melt, and so that the melt might become denser than solid. This was first pointed out by Edo Stoper, a 1981 paper. Basalt melt starts from here compared to olivine density. Olivine is denser than basalt, that's why basaltic melt goes up. But if he calculated the depth variation of density of olivine and melt, Olivine density doesn't change so much because olivine is so stiff. But melt is so soft, density goes up crazy way. Okay, so this is one very important reason why melt density could become very high. Plus, the chemical composition also plays a very important role in determining relative density, such as iron. If iron goes to melt, density is high. But if water goes to melt, density is low. So there are some complications. There are some experimental tests for the Stolper hypothesis done by Carl Agee a long time ago, followed up by Agee Otani, largely confirming the prediction of the Stolper that melt density goes up with pressure much faster than solid density, and therefore at a certain point there's a possibility of density crossover. Of course, this also depends on the composition, which, as I mentioned to you earlier. For instance, if melt is iron-rich, density tends to be much higher than iron-poor melt. And there are some complexities in terms of the influence of composition. Iron tends to go to the melt under the old conditions, makes melt dense, but because of the very fact that melting in the deep mantle occurs only because of the presence of volatiles. Volatiles do go into the melt to make melt density lighter. So there's a very delicate balance between ion effect and volatile effect. We spent some time in my lab to find out the competition. Briefly, there is very strong competition between iron and water, and as a consequence, the melt tends to be dense when partial melting occurs in a deep mantle at relatively high temperature conditions in the general environment. When melting occurs at high temperature conditions, not much water goes to the melt. So therefore, melt is dense. But if melt is formed under relatively low temperature conditions, then lots of water goes to the melt. That's the only way to make a melt at low temperature conditions. In these conditions, melts might be lighter to make volcano originating from transition zone, for instance. Geophysical evidence for partial melting. There are a few observations. One is the seismic velocity drop at the lithosphere-atmosphere boundary, which is often attributed to the presence of melt. And also, recently, there are some observations from the electromagnetic induction studies to find out some high conductivity layer corresponding to atmosphere. And then question is, are those low velocity and high conductivity, are they the results of partial melting or some other processes? There are some other observations in the deep mantle. One is the report by Tozin et al., published about 5 years ago, showing evidence of low velocity regions above 410, which is nearly global. Those are body wave studies, those cannot cover completely global areas, but as far as they investigated, majority of regions, they have some evidence of the low velocity layer, just above 410 kilometer. And there is also a recent paper by Schwandt et al. Showing evidence of the low velocity region below 660, not 60, but 730 kilometer or so. And those are, as I said earlier, the plausible regions where melting might occur, caused by transport of water-rich material from transition zone. So the question is, given those anomalies, are these anomalies really caused by partial melting or subsolidus mechanism? Obviously, partial melt causes low velocity because melt is soft, and then melt has high conductivity. But also there are some subsolidus mechanisms which could explain those anomalies, like a simply high temperature causes low velocity and high conductivity, and hydrogen can also reduce velocity, make material, hydrogen makes material soft and high conductivity. So those are competing processes which we need to evaluate which one is a more likely cause for those geophysical anomalies. And if you look at the history, there are a couple of papers published about 50 years ago, time most of you guys were not born. This is Kanamori paper. This is the year in which he got a PhD. So Kanamori PhD must be mineral physics PhD. He did the measurements of the velocities in those alloys across the melting, partial melting, and they found that even the small amount of melt could reduce the seismic wave velocities dramatically, 10% or so. 4 years later, in the US, Spätzle and Anderson did very similar experiments, ice and the sodium chloride, finding that even the small amount of melt could reduce the velocity 10% or so, very dramatically. Those gave us the feeling that a tiny amount of melt is enough to create low velocities. However, some 10 years after, very important paper was published by Stock and Gordon from Yale University, pointing out that influence of partial melt, influence of melt on elastic properties is extremely sensitive to the geometry of melt. And then pointed out that you need to characterize what kind of geometry, that is the wetting angle. Okay? If wetting is complete, then very tiny amount of melt completely wet grain boundaries, and therefore you can imagine very large degree of velocity reduction. But if tiny amount of melt is just isolated, those isolated melt wouldn't affect. So that's a key point. But then he did some simple experiments and conclude that the influence of melting on physical properties depends strongly on melt geometry, and all previous studies before Stocker-Gordon used materials with zero dihedral angle. So therefore, if dihedral angle of Earth material is not zero, those results cannot be applied. So this is a very important statement. And then several people went to the lab to determine the dihedral angle. And Harvey Wolf and Dave Kohlstedt did those studies, and we also spent some time to determine dihedral angle. And interesting results from my lab is when you measure dihedral angle at low pressure, quite large, but not as large as 60, so the modest wetting melt geometry is tube-like, but dihedral angle systematically changes with pressure, and at certain pressure, dihedral angle becomes so low. So in those conditions, when dihedral angle is indeed zero, then even a very small amount of melt can reduce the velocity dramatically. But in contrast, in those shallow, typical asthenosphere conditions, the dihedral angle is not zero. And therefore, with a very small amount of melt, reduction in seismic wave velocity should be very minor. I already discussed this, so I'm not going to discuss it anymore. But fraction of the melt we expect for the upper mantle is very small. This is the unrealistic case of no gravity. But even with gravity, you can easily calculate the melt you expect. Amount of melt you expect is very small, simply because melt migration is so fast. Mark Spiegelman did very nice work to confirm this from the geochemical observations 23 years ago. So bottom line is amount of melt we expect in many places, including asthenosphere, is very, very small. So there's another very interesting result to show kind of negative evidence for partial melting as a result of MELT project. So this project was to study melt distribution. They went to Eastern Pacific and then determined the various measured the various seismic properties, including anisotropy. And prediction is if the anisotropy is caused by aligned melt, then direction of the fast Chavez spreading is going to be parallel to ridge axis. This is top view. In contrast, if the anisotropy is caused by olivine preferred orientation in solid state, you expect the fast direction is normal to ridge axis. then what they found was, indeed, in the majority of cases, the fast shear wave direction is normal to the ridge, which is evidence against the presence of large amount of melt, which caused the seismic anisotropy. So either melt is located in very focused, narrow regions, or amount of melt is very small. So this is the one observation against partial melt. Then when you learn this, then you may think that, yes, indeed, on average, melt fraction is very low, but there might be some processes to make the local or regional concentration of melt higher. For instance, if melt is accumulated, you expect certain melt-rich layer. Also, this is Kawakatsu-san and Takei-san's paper, suggesting that there might be thin layer in which melt fraction is much larger than average. In these cases, you may expect quite large influence of the partial melting on physical properties. So let's check if those models are consistent with observations. For instance, for this layered model to be consistent with observations of relatively large velocity drop, you must have the very unique porosity in the melt-rich band. For instance, if the background porosity is 0.1, then porosity or melt amount in the band has to be 14.3. If it's 15, you have a 20% velocity reduction. If it's 13, you have a 2% velocity reduction away from the observational constraints. So therefore, this model, in my opinion, is really hard to reconcile with the, unless there is a theory to predict that melt fraction in the melt-rich band is 14.3. Another problem is that this model predicts that velocity reduction at the lithosphere sensor boundary agrees with the seismic anisotropy between SH and SB. And therefore, if you attribute velocity drop to this layer, you must have SH-SV anisotropy with 5 to 10%, which, in my understanding, is not quite consistent with the seismic observations. How about the electrical conductivity? If you have a melt accumulation, you expect the peak in the conductivity. But if hydrogen mechanism is correct, you expect something like this profile. So there was a project. This is no melt project, like anti-melt project. They went to typical 70 million year old Pacific, and they found pretty smooth profile of conductivity based on very dense array. Okay, and then this is in a way not consistent with the idea of melt accumulation at the lithosphere sensor boundary, at least in this region. In terms of subsolidus mechanism, if you could explain lithosphere sensor boundary and then relatively large velocity drop by invoking relatively large jump in hydrogen content caused by partial melting. So in a way, velocity drop like this is indirect consequence of partial melting, not direct. Then you can come up with a model to explain lithosphere senosphere velocity profile. In the deep mantle, as I said earlier, like above 14 kilometer, low velocity regions are detected. This might correspond to complete wetting, which we demonstrated in our laboratory. At those conditions, even small amount of melt completely wet grain boundaries, and therefore this might be the due to small presence of small amount of melt. Let's go to electrical conductivity business, because we heard a few talks commenting about electrical conductivity. Again, observation is there is a high conductivity layer in the asthenosphere, and sometimes they report highly anisotropic conductivity, high conductivity along the plate direction. And the question is, can we explain this by partial melt model or subsolidus model? There are two possibilities, as I mentioned. Hydrogen enhanced conductivity, as is shown in my laboratory for the last 10 years, hydrogen effect is quite enormous. If you go from dry to pretty water-rich environment, conductivity can change by a factor of 100. But melts also have, in general, much higher conductivity than minerals. So therefore, presence of melt may also be the cause of the high conductivity. There was the interesting paper to evaluate the hydrogen model versus partial melt model published 3 years ago, in which authors calculated expected conductivity, expected water content from the hydrogen model and expected melt fraction for partial melt model. And they concluded that with the hydrogen model, to explain observed conductivity, one would need this much water, which is much higher than the water content we expect in atmosphere. So therefore, they rejected the hydrogen model. However, if you look at the partial melt model, the amount of melt that they need is this range, 2, 3, 4%. That is much higher than the amount of melt which we expect in the atmosphere. So therefore, I conclude that both hydrogen model and partial melt model have very serious difficulties in explaining those observations. Then I'm going to show you in the next a few slides that calculation of water content based on limited laboratory data is not quite justifiable, because what they did was they used low temperature data of conductivity, then extrapolated to the atmosphere temperature to conclude that conductivity you predict is too low, so therefore you need lots of water. I would argue this extrapolation is not quite appropriate if you look at a little bit of physics of the electrical conductivity. Point is, properties such as electrical conductivity, if you plot against 1 over temperature, this is a low temperature range, the high temperature range. And then earlier studies were conducted at low temperature range because they didn't want water to go out from your sample. Okay, high temperature, quite often water goes out from your sample. So they limited their measurements to low temperature. However, if multiple mechanisms exist, then extrapolation of low temperature to high temperature range is not justifiable. Like if you extrapolate like this, you would calculate this much of conductivity, but if the mechanism change occurs like this, actual conductivity is much higher. Okay? So the extrapolation is not justifiable if conductivity mechanisms change. So therefore, you need high temperature measurements of the electrical conductivity. So we spent some time in my lab to do new measurements at much higher temperature conditions with some technical developments. And those results are compared in this diagram. All the data are here, low temperature range. They agree more or less within the uncertainties. But in addition to covering the temperature range covered by all the studies, we also conducted experiments at much higher temperatures. Then you can see quite clear evidence that at high temperatures, trends are quite different in 2 ways. One is the slope is different, which means activation energy is different, new mechanism is operating, and another important observation is low temperatures range, anisotropy is almost 0. Very isotropic, but at high temperatures, anisotropy is very strong. Okay? So therefore, the extrapolation of the laboratory data of conductivity from those low temperature regime to high temperature in atmosphere temperatures here is not justifiable. And then if you use those high temperature results, you can explain both the magnitude of conductivity by plausible temperatures and water contents in the atmosphere, which is consistent with geochemical inference, as well as the anisotropy. Okay? So I would argue that the hydrogen-assisted conduction model explains both the average high temperature and highly anisotropic conductivity of atmosphere. If you were to explain those by partial melt, you really need to have certain melt amount, a certain way of alignment of melt. which you might be able to do it, but without those very ad hoc, I would say, assumptions, you cannot explain those observations by partial melting. So indirect measurements, inference of melting is one way, is like lithosphere asthenosphere. My interpretation is the velocity drop at lithosphere asthenosphere boundary is caused by hydrogen layering, which is formed as a result of partial melting at the near mid-ocean ridges. And also the, in terms of electrical conductivity, if you look at the global plots, you can see substantial increase in conductivity in the transition zone depths, as opposed to what you expect from laboratory data for constant water content. If you assume constant water content, like 0.01 for green, conductivity must drop at the 410 boundary. But the observation shows jump, which means, in my view, there's a jump in water content. So that is my interpretation of conductivity profile, which might be the result of the partial melting near 410 kilometers. So to summarize, with some volatile, partial melting is ubiquitous throughout the mantle, and partial melting produces compositionally different materials, melts caused by melt segregation, which causes, of course, the chemical evolution of this planet. And if the melt segregation is efficient, and if the melting is just caused by volatile, melt fraction you expect is very limited. And so therefore, direct detection of partial melt by geophysical method is going to be very difficult. But however, under those conditions where melt completely wets grain boundaries, then you could do it. So therefore, it is very important to conduct laboratory experiments to study dihedral angles, as we did several years ago. This study must be extended to transition zone and lower mantle conditions. In regions with, where melt does not completely wet grain boundaries, indirect detection of partial melt might work. One example is the lithosphere asthenosphere boundary, and some other regions, if you have some inference of the chemical layering, that is a very strong evidence for partial melting, because chemical layering is impossible for the convective mantle without large-scale segregation of the materials. I think I should stop here. Thank you very much.
Questions for Shun? Rich?
I have a couple of questions. The first one is about the density differences. So when you have, well, you showed a solidus for the deep mantle, which had a positive slope. As you increase the pressure, the temperature of melting increases.
Yeah.
And then, you know, the argument of having a denser melt,
Yeah.
is that consistent with the Clapeyron equation?
Clapeyron equation, to argue this, works only for single phase. If you have a multi-phase, it doesn't work.
Well, two phases are minimum because you need solid and melt. No? Or you
mean
mean
component.
multiple solid phases?
Yeah, so if you have a single phase, just melting temperature, okay,
Yeah.
then you can apply the delta B, delta S.
Yeah.
But if you have multi-phase, the chemical segregation occurs. And therefore, direct application of Clapeyron slope to infer delta B is not possible.
Okay.
And yeah, even worse, actual melting in those conditions occurs due to volatiles. The solidus I showed is the dry solidus.
Uh-huh.
So yeah, I see what you're asking, but I think in case of melting in the multi-component, second with volatile, yeah, inference from solidus is not bad.
Okay.
I mean,
I'm wondering what are the constraints on the depth of the density crossover?
Constraints on, oh, okay. I have one partial answer. Okay, we studied density crossover conditions for like a 410 kilometer. Okay, and then for this case, 410 kilometer, either density crossover occurs or not depends on the temperature at which melting occurs. Okay, so yeah. So therefore, if you ask a question at which depth, it really depends on the conditions where melting occurs, and then this will shift.
Would the observation of attenuation help in distinguishing between subsolidus mechanisms or partial melting responsible for some of the...
Yeah, that's a good question. Actually, earlier this workshop, we had some discussion. Doug made a very interesting, answer is yes. If you have very detailed measurements of attenuation, particularly QS and QP. Bulk attenuation is very unique to materials containing melt. And if you have evidence of very large substantial bulk attenuation, this is very strong evidence for the presence of melt. Yeah.
You mentioned the LAB, so do volatiles appreciably impact the seismic velocity?
Yeah, my model is at LAB, number one, there is the layering in the water content. And that affects physical relaxation processes. So the answer is yes. In my model, volatile enhance the relaxation process to make velocity lower.
Yeah, so just remembering that the LAB is sensed by body waves that are at higher frequency compared to surface waves, for example. So the attenuation effect should be less. I don't know where you are in that curve, but yeah, right.
Yeah.
Elastic effects.
Yeah, but when I developed model to explain body wave data, yes, my calculation is based on like 1 second. Yeah.
Any further questions for Shun? In which case, can we just thank Shun again? Thank you very much.